In this video, we shall see the another type of power amplifiers, that is class B push-pull power amplifier. So this is the circuit diagram of class B push-pull amplifiers. You can see now. So this is M1 is a MOSFET. So this is the load resistor. So we know that the class B power amplifier is a second category of power amplifiers where the conduction angle is only 180 degrees, meaning this class B power amplifier is not at all biased. So this MOSFET will turn on when the input voltage is above 0 voltage. If it is less than 0, the MOSFET is off. So that's what is seen here. The output follows the input only during the positive half cycle. During the negative half cycle, the MOSFET is off. So that's why the output voltage is 0. It is always better to observe, even though it is said as it will want to conduct for the entire 180 degrees, but as long as the input voltage is less than the threshold voltage of this MOSFET, the MOSFET is off. That's why you can see. So if you zoom this particular portion over here at the zero crossing, so till the input voltage is, if the input voltage is less than V threshold, the output becomes 0 here. You can say, of course, during negative half cycle it is 0 because the input voltage is less than threshold voltage. So it happens when the input voltage is less than the threshold voltage, the output will be 0. So even though it is not conducting for the entire 180 degrees, the conduction angle, since the threshold voltage what we are considering, which is 0.4 or 0.5 volts, so which will be very less compared to the input voltage, because we know that for the power amplifiers, the input voltage is very large. So as V threshold is very small compared to V in, so because the V in is very large value, we still consider the conduction angle is approximately equal to 180 degree. But theoretically speaking, the conduction angle is slightly less than 180 degrees. But considering the magnitude of the input voltage and the threshold voltage, we write it approximately equal to 180 degree. Now, as we can see now, the input voltage is a pure sine wave, but at the output we have only the half wave form. So which is not a useful one. So we know it is not a useful because it has got only the half wave signal. So there's a lot of distortion in this sine wave form. So we need to have a distortionless sine wave as a valid output. Meaning to say, this class B amplifier in this fashion is not of any use because we are not getting the other half of the input waveform. So we'll go for the modification of this class B power amplifier. Now this is the modification. As you can see now, this is class B push-pull power amplifiers. The name push-pull is coming due to the two MOSFETs of opposite type. That is, one is NMOS, the other is PMOS. Now during positive half cycle, the input voltage, the M1 conducts. During the negative half cycle, M2 conducts. As we can see here, so the output voltage is 0 here because the input voltage is less than threshold. So as the input voltage goes above threshold, you can say output is almost following the input. The same thing happens for the negative half cycle. We can see actually we expected a pure sine wave. Now we can see there is a distortion happening at the crossover of the input voltage at 0. So this is named as crossover distortion. So this crossover distortion will occur whenever the input voltage crosses 0 here. Now you can see now this is the transfer characteristics of this class B push-pull power amplifiers. Now, if the input voltage is less than threshold or less than minus threshold, the output is 0. Otherwise, output follows the input. Now, the slope is 1 here. So, class B push-pull amplifier is giving a sine wave with small amount of distortion. If we can neglect this distortion, then we can see the waveform is a sinusoidal waveform. So, let us try to see what is the power conversion efficiency of this class B push-pull power amplifiers. Now we have the power conversion efficiency. It has been by PAC by PDC. That is the AC power delivered to the load and the DC power consumed by the circuit. We know that the output waveform is somewhat like this. Now, even though there's the distortion, we are assuming that this is not affecting too much. Now you can say this goes up to the peak goes up to VDD and this goes up to minus VSS. Assuming this VSS is almost equal to VDD, so it is a swing is 2 VDD. Neglecting the crossover distortion, the output is almost like a sine wave. with peak voltage at VDD, then power delivered to a load of RL is given by, that is Vs is equal to V naught RMS square by RL. That is RMS square, output voltage RMS square divided by RL happens to be the AC load that is delivered to the load. Now RMS is nothing but output peak by root 2 is your RMS value, that whole square by RL. We know that V naught peak, which is nothing but approximately equal to VD. So upon substituting that, the AC power delivered to the load is given by VDD square by 2RL. So this is the power that is delivered to the load, that is the AC power delivered to the load. So let us also have a look at what is the power that is being consumed from the power supply. Now we can see, to find PDC, of course there is no biasing given to M1 and M2. So M1 will be conducting only during the positive half cycle of the input voltage, and M2 will conduct only during the negative half cycle, because as you can see in the previous circuit diagram, so this input is given to commonly to both M1 and M2. So during positive half cycle of the input voltage, M1 conducts; during negative half cycle, M2 conducts. Meaning at any point of time, any one MOSFET is conducting, meaning during positive half cycle only M1 conducts, during negative half cycle only M2 conducts. That means to say, the DC power that is consumed, so is nothing but the power drawn by M1 during the positive half cycle, and how much is the power that is being drawn by M2 during the negative half cycle. So power will be drawn from VDD. The M1 is going to draw the power from VDD, and that is nothing but the DC current that is drawn from the supply source by the M1 multiplied by the voltage, and again it is due to M2, that is IDC, that is the drain, the DC current drawn by the M2 multiplied by the corresponding voltage. Now we know that this is IDCM, that is the DC current flowing through MOSFET 1. So it is very clearly evident that the DC current will flow only during the positive half cycle. Now this is like a half-wave rectified signal. The peak amplitude will be VDD by RL. So whatever current that is flowing is due to the peak and the RL value, as we can see here now. So this is VDD and this is the ground. The current flows in this direction. So neglecting the resistance of this MOSFET, the current flowing through this path is nothing but VDD divided by RL. So the peak current that is flowing through the MOSFET during positive half cycle is given by this VDD by RL. So that's what is the magnitude. So this is the magnitude is VDD by RL. Similarly, for the magnitude of your current flowing through M2 is VSS by RL. So this is the magnitude. Now we know that if it is a half-wave rectified signal, something like this, the DC current is given by the I peak by, so we usually write it as Im by pi. So Im by pi is nothing but I peak divided by pi. So I peak in this case is nothing but VDD by RL. So this is I peak divided by pi. So meaning the DC current flowing through each of the MOSFET is VDD by VDD divided by pi into RL. So which is same in this also, it is VSS by pi RL. So now we end up in, now we can see this is the amount of power being dissipated in MOSFET M1. This is the power dissipated in MOS M2 during negative half cycle, positive half cycle. Assuming Vs is equal to VDD, we can write the power that is being dissipated by both the MOSFETs during the entire cycle is given by the summation of these two, that is 2 VDD square by pi into RL. So once we know what is PDC, that is power that is being consumed by the two MOSFETs during the entire cycle, and we already found out, okay, what is the AC power that is delivered to the load, which is given by VDD square by 2RL. So upon substituting those PAC by PDC, so we get the value of conversion efficiency as pi by 4, which is 78.5%. Meaning to say, if we are having a MOSFET, which is each of the MOSFET, if it is conducting for 180 degrees, the power conversion efficiency of this type of class B push-pull amplifiers is very good compared to the class A amplifiers. Normal class A amplifier has got a efficiency of hardly 25% theoretical, and using the transformer coupled, it was increased to 50%. Now you might have observed that in the transformer coupled or in the class A amplifiers, the MOSFET was biased so that the current was flowing through that the entire cycle. But here in this case, each of the MOSFET is conducting for only half of the cycle. So that's why this PDC has reduced. So now PDC is 2 VDD square by pi RL. So this reduced value of PDC will going to certainly increase the efficiency of the class B push-pull amplifier. So this way, this class B push-pull amplifier is certainly having some crossover distortion, but it is giving a better power conversion efficiency from 25% of class A ordinary to 78.5%, and in class A push-pull we had around 50% efficiency, but in class B, in class A transformer coupled it was 50%. In class B push-pull power amplifiers it is 78.5%. So in most of the output stage, so class B push-pull is used, which is having a efficiency of 78.5%.